Well, thank you. All right, so we're going to do oxidative phosphorylation. Oxidative phosphorylation takes place on the cristae. The cristae are the inner folding of the inner mitochondrial membrane. Okay? So, when I told you that it's broken up between electron transport chain and chemiosmosis, what the electron transport chain is, it is a series of enzymatic proteins that are embedded on the mitochondrial membrane. Just like what you learned about membrane proteins, same premise. Same premise with membrane proteins and diffusion and all of that lovely stuff that you just learned in the last chapter. So we got one protein complex there, two, let's draw a protein complex here, three, and I guess a red one right here, four. There you go. There's your protein complexes. This is the electron transport chain. Now, the biggest, baddest guy, he is called the ATP synthase. The ATP synthase is this big enzyme here. So let's go ahead and label it up. ATP synthase. What does ACE mean? Nobody wants to answer because you're on video. ACE means it's an enzyme. Enzymatic reactions are going to happen there. There's your ATP synthase. That is the site of chemiosmosis. So this electron transport chain, this ATP synthase is the site of chemiosmosis. I know what it looks like. All of these together are oxidative phosphorylation. Okay? Alrighty. So, kind of going back to here, I already told you that this oxygen, when this oxygen comes into the mitochondria, it breaks into two oxygen atoms. And when it breaks into two oxygen atoms, that means its valence is no longer full and it's searching to pull on some electrons, okay? It's searching for electrons. So what the oxygen does, it will go to the end of the oxidative phosphorylation and it will start, it goes to the end of the electron transport chain, starts pulling on electrons that are coming down the electron transport chain. Well, these electrons are going to come from these molecules, NADH and FADH2. So your NADH is going to release hydrogens, boom, boom, hydrogens. I'm just going to throw some hydrogens out here because we have a lot of hydrogens being released from your 10 NADH molecules. Your NAD plus is going to go get recycled back over there. NAD pluses, 10 of them, they're just going to go back over here. They're going to be needed. And then you have electrons, which I should be doing in black. Electrons get released, boom. And by the way, these electrons are high energy. They're highly energized because they came from the original high energy glucose molecule. Oh, there. I wish I had, I do have an orange. Let me do orange instead. It's like glowing. Boom and boom. Oh, where's my orange? High energy electrons at the beginning, i.e. top of the electron transport chain, okay? Same thing happens with your FADH2, except your FADH2 will not react with this enzyme. It's going to react with enzymatic complex here, number 2. This is enzymatic complex number 1, this is enzymatic complex number 2. And the reason why is because it's a different molecule, so thereby it needs a different enzyme in order to facilitate a reaction. So it's going to release electrons, it's going to release H's, boom, H's, H pluses, and so forth. It's going to release the FAD molecules to go get recycled back in citric acid cycle. And then it's going to release, I'll just go ahead and draw those there, high energy electrons. I'm not going to hold you to how many electrons and how many hydrogens, okay? At some point in your career, you might have to. Alrighty, so these highly energized electrons are going to travel the electron transport chain. This is going to travel the electron transport chain because down here, the oxygen is pulling on them. The oxygen protons are pulling and pulling. And so when they get down to the bottom of the electron transport chain, they're low energy because what's going to take place as these electrons travel the electron transport chain, they are going to transmit some of its energy to the enzymatic proteins. And those enzymatic proteins are then going to pump the hydrogens across the membrane. Boom. Every time it travels, these hydrogens pump across the membrane. And you start building up a high hydrogen concentration because you're pumping all these hydrogens across the membrane. Boom. High hydrogen concentration. Now this one right here does the same thing, except it starts on cytochrome complex number 2. And then so it is going to travel, electron transport chain, pump hydrogens across the membrane, building high hydrogen concentration. And then it travels, and then it travels, and then you have low energy electrons. I'm just going to go ahead and point because it's getting busy. So we just know high energy electrons at the top of the chain. As they travel those enzymatic proteins, those enzymes will remove some of that energy. They will use that to produce a proton motive force, which will push those hydrogens against their concentration, trying to build up a high concentration in the inner membrane space. So this is matrix. This is the inner membrane. This is the inner membrane space. I didn't label it because I needed to work in here. So what's going to happen as you start building a high concentration of those positives, they don't like it. They got a high energy value. They got to get out of there. They just want to get out of that space. There's too many positives. So what's going to happen is those hydrogens will just naturally diffuse down their concentration gradient through the ATP synthase, going from a high concentration of hydrogens towards a lower concentration of hydrogens. They'll just go through the ATP synthase down their concentration gradient. When they do that, it causes this enzyme to have a shape change. Hydrogen comes through, shape change. Hydrogen comes through, shape change. And when it has that shape change, I gotta move these guys, they're in my way too. I'll put them right here. Boom. You have ADP molecules sitting and waiting, along with some P molecules. Some P inorganic atoms. Then, because of the shape change, this enzyme will help to hook together those, making ATP, just like such. And through oxidative phosphorylation, you get 26 to 28 ATP. So, you see why it's the biggest, baddest one, right? So let's write that down here. I gotta write it right here. 26 to 28 ATP molecules made in oxidative phosphorylation. So total, 26 plus 2, 28, plus another 2 is 30. So out of all of cellular respiration, you get 30 to 32 ATP total per one glucose molecule. Per one glucose molecule. We're not done. We're almost done, but we're not quite done. Because this oxygen is sitting out doing its own little thing, right? Well, this oxygen, when he pulls on these electrons, let's go ahead and get his arrow. When he pulls on those electrons are low energy value. They gave all their energy to the electron transport chain. I'm sorry this is ugly, but we got videos and you guys got your book. They release their energy to the electron transport chain. Low energy electrons, all you could do is go off with an oxygen molecule and 2 hydrogens and make water. H2O. Oxygen plus electrons plus 2 hydrogens. Water is cellular waste. So if we write out our little formula, let's check off our little formula. I don't know where I can write it, nowhere to write. I'll write over here. Oh, I'll write it long ways. Cellular respiration, C6H12O6 I can't do that. I'm just gonna have to get on a chair. I'll do it up top. This is weird. I'm getting in the way. Alrighty. C6, H12O6, sugar, check. Oh wait, I don't want to check on there. Check, plus oxygen. Look at that, oxygen. 6 O2 molecules. Going to yield carbon dioxide, 6 CO2 molecules. Look at that, CO2 molecule here, 4 of them. CO2 molecule here, 2 of them. 6 total, check. We don't have to count off how many of the oxygen, I'm just letting you know that, there you go. Plus water, 6 water molecules. Look at that water being released, check. And ATP is the product, cellular, used for cellular energy. ATP, 26 to 28, 30 to 32 total. Now we're done. Go ahead and pause it. It's good, it just looks ugly.